Good morning. So welcome you back to the course MA4832 on microprocessor system. Today we are going to study lecture 3, which is about the data representation. In lecture 1, we have studied ARM architecture. It is for you to appreciate the hardware aspect of the microcontroller that you are going to use during your hands-on practice. In lecture 2, we have a study ARM memory. This is for you to understand the usage of the memory for the storage of instruction and for the storage of data. In lecture 2, we have show you some typical example which relay instruction program to the memory content and the memory location. So it is very important for programmer to know what happens when you execute your program. And today we are going to answer another question. You may have this question in mind, how to represent value or data inside the memory. Then from today's study, you should be able to answer this question. So today's study is also very important to programmer because the function of your program is basically to read in data, process data, and output data. Therefore, you must know how to represent data inside the memory of a microcontroller or microprocessor. So before we enter the study of today's content, let's have a quick overview about the answer to these 4 questions. Question number 1, what is the motivation for you to study this course? Question number 2, what is the objective for you to study this course? Question number 3, what are the content that you are going to study from this course? And question number 4, what is the methodology for you to follow in order to become a good programmer of microcontrollers application? Okay, so this slide shows you the answer to the first question. There are 2 motivations for you to study this course. Motivation number 1, if in future you are going to design smart system in which they will be closed-loop control system, then you need to incorporate microcontroller to serve as one of the basic 3 building blocks inside a closed-loop control system. Motivation number 2 is if in future you are going to design smart communication device, then you must make use of a microcontroller to serve as a node inside the communication network. So it is quite important for you to have a good understanding about the use of a microcontroller. If in future you will be working as an engineer, okay, in these 2 type of application, okay. And this slide basically shows you 2 typical examples of a smart product or smart system. And for question number 2, what is the objective for you to study this course? The answer for you is the objective for you to study this course is to become a user of a microcontroller. So we are not expecting you to become a designer of a microcontroller, okay? As a user, then you must know the problem that you are going to solve, and you must also know the solution or algorithm behind the problem, okay? So then your objective is to implement your algorithm or implement your solution on the microprocessor system or microcontroller. So you need to know how to use microcontroller or microprocessor system to implement your solution, to implement your algorithm. Question number 3, what is the content that you are going to study from this course? This course consists of 2 parts. The first part is about the programming. The second part is about the interfacing to input and the output device. I will teach you the first part, and Prof. John Han will teach you the second part. The question number 4 is, what is the methodology for you to follow in order to become a good programmer of a microcontroller? So this slide basically shows you the answer. So as a programmer of a microcontroller, you must focus on the use of a register. And the primary job of a programmer of a microcontroller is to determine the right value for right register. As long as you are able to determine the right value for right register, then you just use one of these 3 instructions to set the value to the register. Okay, so of a reading value from register or writing value to register, this action will be extremely simple. You just need to know how to make use one of these 3 instructions. So it is not a big deal, okay? But pay attention, the challenge is for you to understand the content of all the register related to the microcontroller. So that is a challenge because this microcontroller has a lot of register, okay? But the good news is you do not need to memorize all this because we have a reference manual. And if you've forgotten something, you can always refer to the reference manual, okay? But your focus is on the understanding of the content of each register and know how to use each register, okay? Or how to determine the value for each register based on the requirement of your own problem or your own application, okay? So there's no universal answer because different user may have a different application, different problem, okay? So you just need to know based on your problem, your application, or your own requirement, then you must know how to determine the value for each register involved, which are involved in the implementation of your application. Clear? Okay. So focus your attention on the property and the content of this register. Okay. So today's study is very important because we need to know the answer about this question: how to represent data inside the memory of any digital computer, which include microcontroller. Okay. So today's lecture basically will provide answer to you. Okay. Then with this answer, then you will be confident about the use of a microcontroller. Okay. So let's start with a binary number. Because digital computer at the lowest level can only compute binary number. This is because digital computer can only understand value 0 and the value 1. Okay, this is shown by this hardware. For example, input is 1, then output will be 0. If input is 0, then output is 1. Okay, so this is a typical behavior of a digital computer. So therefore, we must know, okay, what is a binary number system? It's because our digital computer only understand binary number. Okay. Then first question, what is the format of a binary number? So binary number consists of a series of a digit. Then in this case, it's a binary digit. Okay. And each digit has a value and has a position. Okay. Then the exact value of a digit is equal to the value of the digit times the value indicated by position. Okay, so this is a way for us to produce, okay, a final value based on the use of the digit, okay, which are aligned in series. For example, we have a series of a digit like this: 1110011, 11000111. By convention, the digit in the left-hand side has a smaller value than the digit in the right-hand side. This is why, to the extreme end of the left-hand side, we name this one as the digit of least significant bit. Okay, so this significant digit, and the digit toward the extreme of the right-hand side, we call this digit as the most significant digit or most significant bit. Okay, so these are the two terminology in digital computer: the least significant digit, the most significant digit. All right, okay. Then how to evaluate the value, the final value of a series of a digit? The answer is here. Okay, so this is the equation. The value which represented by a series of a digit is equal to the sum of value represented by each digit. Then the value represented by each digit is equal to the multiplication of the value of a digit itself times the value of the digit's position. So, for example, this digit is a position n minus 1. Then the value from the digit's position is equal to 2 raised to the power of n minus 1. Therefore, the value of a digit itself times the value of a digit's position. That gives you the value represented by this digit. Then we add them together, then we get the sum. And this sum is equal to the value represented by the series of a digit. So we have a series of a digit. For binary system, the value of a digit is equal to 0 or 1. Okay? And the position of a digit could be positive. Positive means if the position is in the right-hand side of a decimal point. But later on, we'll show you what is a decimal point. Okay? In the right-hand side of a decimal point, then the position are positive. If it is in the right-hand side of the decimal point, then the position are negative. Okay, so positive position will allow us to represent integer. Then negative position allow us to represent fraction. All right. So here I show you some example. For example, this is the least significant digit. This is the most significant digit. Then we start from this digit first. This digit has a value 1 and the position 0. Then the final value represented by this digit is equal to 1 times 2 raised to the power 0. Then you get the 1. Okay. Then for this digit, the value of the digit itself is 1. Then the value of the digit's position is equal to 2 raised to the power 1. Then we have a 1 times 2, then you equal to 2. Then you evaluate this one. The value of the digit itself is 1. The value of the digit's position is 2 raised to the power 2. That is equal to 4. Then 1 times 4 equal to 4. Then you get the 4. Then for this digit, the value of the digit itself is 1. Then the value of the digit's position is equal to 2 raised to the power 3. And which is equal to a. Then 1 times a equal to a. Then you lump all this together and compute the sum of these 4 values. Then you get the final value, which is represented by this series of digits in binary system. Okay. From this example, you will see the value at this position is equal to 2. Value at this position is equal to 1. Then this statement is true. 1 digit in the left is 2 times the digit in the right. Okay. Okay. So then for this example, I guess you can easily work it out. Okay. what is the value from this digit? So the value from this digit is equal to the digit itself times the value of this digit's position. This is the position 7. So it's 1 times 2 raised to the power 7. Then is equal to 128. Then for this one is equal to 1 times 2 raised to the power 6. Then you get the 64. For this one is equal to 1 times 2 raised to the power 32. Then you power 6. This 765 power 5. Okay. Then you get 32. For this one is equal to 1 times 2 raised to the power 4. Then you get the 16. Then add them together. Then this is a value represented by this series of digits. Okay. These two I let you to verify that, so you should be able to get this result. Okay. We may also have a digit in the right-hand side of the decimal point. Okay, you see this dot. This is a decimal point. Okay. Then in this case, this is a position -1, position -2, position -3, position -4, position -5. Then what is value represented by this digit? So it's equal to 1 times 2 raised to the power -5. Then you will get this number. What is the value correspond to this digit? Answer is 1 times 2 raised to the power -6. Then you get this one. Then what is value correspond to this digit? Answer is 1 times 2 raised to the power -7. Then you get this one. Then what is value correspond to this digit? Answer is 1 times 2 raised to the power -8. Then you get this one. Okay. So you follow the same principle, then you should be able to verify the result for this series of digits, this series of digits, this series of digits. Okay. So here I show you the intermediate result, then you should be able to verify. Okay. Once we know how to represent by number inside the memory, then next question will be how to do the computation with such representation. Okay. So let's look at the addition. For example, we have a 2 input, then the sum of the addition will be the output. Okay, so the 2 input plus 1 output, all of them are represented by a series of digits. Okay, so mathematically they could be written in this way. Then we need to know how to determine value C from a value A and the B. Then the solution is to follow this rule. Okay, if value A is equal to 0, value B is equal to 0, then value C is equal to 0. If value A equal to 0, value B equal to 1, then value C equal to 1. If value A equal to 1, value B equal to 0, then value C equal to 1. If value A equal to 1, value B equal to 1, then value C equal to 0 with a carry of 1. Okay, so here just show you an example. 5 is represented by a series of 3 bits, that means 1, 0, 1. 3 is represented by a series of 2 bits, is 1, 1. Okay, then we do addition. Okay, 1 plus 1, follow these rules. Then result is 0 with a carry of 1 toward the left-hand side. Okay, then at this position, then we have a 1 plus 0 plus 1. 1 plus 0 equal to 1, then 1 plus 1 equal to 0 with a carry of 1. Then at this position, we only have a 1, 1. Okay, 1 plus 1 equal to 0 with a carry of 1. Then at this position, we only have a 1. Then 1 plus empty equal to 1. Then this is the final result. Okay, so you can verify 5 plus 3 equal to 8. Then this is the binary representation of A. Okay, so this is correct. Okay, this is a correct result. Okay, then one more example. If let's say we have an organ, this is 1 input, second input we call it as an addend. Okay, so then what will be the result? So we add them together. We just do this calculation. Okay, this is the organ, this is the addend. 0 plus 0 equal to 0, 0 plus 0 equal to 0, 0 plus 1 equal to 1, 0 plus 1 equal to 1, 1 plus 0 equal to 1, 1 plus 0 equal to 1, 1 plus 1 equal to 0 with a carry 1. Then 1 plus 1 equal to 0 with a carry 1. Then 0 plus 1 equal to 1. Okay? Then here you have a carry 1 plus empty equal to 1. Okay? But this one corresponds to a carry of 1. Okay? So this is the result. All right? Then how about the subtraction? Subtraction is the same. We have a 2 input. Then we have a 1 output. Then all of them are represented as a binary number. Okay, therefore we need to determine value of a C from value of A and B. Again, we just follow this rule. For example, if A is 0, B is 0, then 0 minus 0 equal to 0. If A is 0, B is 1. Because 0 is smaller than 1, then in this case, result is equal to 1 because we have a borrow of a 1. When we borrow from a bit in the left-hand side, we get the value of a 2 because one position in the left-hand side is 2 times the value at the actual position. So when you borrow 1, actually you borrow a value of a 2. Then 2 minus 1 equal to 1. Okay, this is why you have a 1 here. Okay, if A is equal to 1, B equal to 0, then you have a 1. If A equal to 1, B equal to 1, then result is 0. Okay, so something like that. Then here is the illustration. It's a 5 minus 3 should be equal to 2. 5 is represented by 1, 0, 1. 3 is represented by 1, 1. Then 1 minus 1 equal to 0. 0 minus 1, we cannot do it. Then we must borrow a value, borrow 1 digit from next position. Okay, once you borrow 1 from here, so actually you get the number 2 here. Okay, value 2. Then 2 minus 1 equal to 1. And once we borrow 1, then we must deduct 1 from this. Then 1 minus this 1, then get a 0. Then this is the result. Okay. So in mathematics, this we call is the myrian. This is a subtrahend. Okay. So myrian and the subtrahend. So then we have a borrow. This is a borrow, a borrow of 1. Okay. And here just show you one more example. So we have a myrian like this, subtrahend like this. Then result will be like this. Okay. So we have a 1, 1, 1, 1, 0, 0, 0, 0, minus 1, 1, 0, 0, 1, 1, 0, 0, okay? 0 minus 0 equal to 0, 0 minus 0 equal to 0, 0 minus 1, then we must borrow 1, okay? This is a borrow of 1. Then we get the value 2, 2 minus 1 equal to 1, okay? So then once you reach here, so you see this is the borrow. We must is negative. So then it's like a 0 minus 1 minus 1. Then we must borrow again. Borrow from left-hand side. Once we borrow one value, then we get the value of 2. Then 2 minus this 1 minus this 1, you get a 0. Okay? So once you reach here, we borrow 1, then we have a 1 here, you deduct 1, that means 1 minus this 1, then we get a 0, okay? So we deduct this 1, because this is a borrow of 1, okay? So get 0. Once we reach here, 1 minus 0 equal to 1, 1 minus 1 equal to 0, 1 minus 1 equal to 0, then there's no borrow bit, okay? Actually, here's a borrow, but this is a borrow of 0. So we did not borrow anything, okay? It's empty, okay? So this will be the result of this calculation. Okay, so that's about the study of a binary system. So we can extend the principle of representation of a binary number into the case of a decimal number. So decimal number are the number that we are familiar with, because by default, all of us make use of a decimal number. Okay, this is our default representation or default number system. Okay, so the format of a decimal number, so similar like a case of a binary number. So we use a series of a digit to represent, okay, a decimal number. So a digit is the same, has a value, has a position, because the position also is a representation indication of a value. Okay, then the final value of a digit is equal to the value of the digit itself plus the value from the digit's position. All right, then so here is an example. We can write this value. Okay, 1, 2, 3, 4, 0, 0, 0, 0. Okay, so then the the value represented by this series of a digit should be equal to the sum of a digit's value, and the digit's value is equal to the value of the digit times the value of the digit's position. Okay, so then mathematically it's like this. Okay, so and for each digit in the decimal number system, then this digit could be equal to 0 all the way to 9. Okay, so you have 10 value here. Okay, and the position is indicated by I, could be 0 all the way positive or -1 all the way negative. Okay, if the position is in the right hand side of a decimal number, a decimal point, then the position are negative. If the position are in the left hand side of a decimal point, then I are positive. Okay, then how to evaluate this series of digit? The answer is this one. Okay, the final value is equal to the sum of the value of each digit, and the value of each digit is equal to the multiplication between the value of the digit itself times the value of the digit's position. The value of digit's position in this case for decimal number is equal to 10 raised to the power, which is equal to the position of the digit. So in this case, 10 raised to the power n minus 1. Then for this case, 10 raised to the power n minus 2, etc. All right. So this is a mathematic description of a decimal number, and also it shows the way how to evaluate the final value, which is represented by the series of such digit. All right, and here I just show you 4 practice for you to know how to evaluate, okay, the value of a series of decimal digit. Okay, for example, we have this series of a decimal digit, but everyone knows that this is 2,234. Then how do we know this is a 2,234? We apply this formula. Okay, so this is the position in the left hand side of the decimal point. So it's position 0, 1, 2, 3. Okay, then this result should be equal to the value represented by this digit should be equal to the value of digit itself times the value of the digit's position. So it's equal to 2 times 10 raised to the power 3. Position is 3, then 10 with power 3. So it's 1,000. 2 times 1,000, then it's 2,000. For this one, the value is equal to 2 times 10 raised to the power 2. Then it's 100. 10 with power 2 is equal to 100. Then it's 200. Then you get a 200. Okay. Then for this one is 3 times 10 raised to the power 1. Then it's 30. For this one is equal to 4 times 10 raised to the power 0. Then it's 4. Okay, so you add them together is 2,234. Okay, okay. And also from here you will see, okay, one digit in the left. Okay, this 2 is in the left of this 2 is 10 times the digit in the right. That means this value is 10 times of this one. Okay, so you can easily verify. Okay, then for this is the same. You just do the evaluation. Okay, position of this one is what? position 0, position 1, 2, 3, 4, 5, 6, 7. Okay, should be equal to 6. The value of this digit equal to 6 times 10 raised to the power 7. For this one, 7 times 10 raised to the power 6. This one, 8 times 10 raised to the power 5. For this one, equal to 9 times 10 raised to the power 4. And you get this number. Okay, so you can easily verify the remaining result. Okay. Then for fraction, how to represent fraction with a decimal number? So it's the same principle. Okay, let's say 0. Or this 0.00002234. Okay, so then what will be the value from this digit? Value of this digit is equal to the value of the digit itself times the value at the least digit position. At the least digit position, the value is equal to 10 raised to the power -5. Okay, so you have okay, -5, then you get the 0.0002. Okay, for this one is equal to 2 times 10 raised to the power -6. This one equal to 3 times 10 raised to the power of -7. This one is equal to 4 times 10 raised to the negative power of a. Okay, so then you can easily get this value. Okay, then for the rest you can verify. Okay, so I let you to verify by yourself. Okay, so you follow the same evaluation procedure, then you should be able to get the right value, etc. All right. Okay. Then how's about the computation? If let's say we have two decimal number, we want to compute the sum of these two decimal number, then the result will be a single decimal number. Okay, so all of them could be represented by a series of digits like this. Okay, then in this case we need to know how to determine value C from value A and the B. Again, we apply this rule, okay, in order to determine C. For example, if the sum of the value A plus value B is greater than 9, okay, then in this case, C is equal to A plus B minus 10 with a carry of 1. Otherwise, C is just equal to A, okay, plus B. Okay, here is AI, okay, so I indicate the position of A and the B, okay, etc. Okay, so here just show you example. Let's say 95 plus 16. Okay, so you will see 5 plus 6 is greater than 9. Okay, so immediately we just do this computation of 5 plus 6 minus 10. 5 plus 6 is equal to 11. 11 minus 10 equal to 1. Okay, then with a carry of 1. Then carry of 1 here. Now we have a carry, then we have a 9, we have 1, add them together, so you find out this is 11. Okay, so you must also apply this too. Then 11 minus 10 will give you 1 with another carry, with a carry of 1. Then this carry bit, okay, digit plus empty equal to 1. Then final result is 111. Okay, it's 111. Okay. We must read like this, 111. All right. So here's one more example. Okay. So we have this organ and the aden like this. So 0, 0 equal to 0, 0 plus 0 equal to 0, 0 plus 9 equal to 9, 0, 0 plus A equal to A, 9 plus 0 equal to 9, A plus 0 equal to A, 7 plus 4. Now you see exit 9. Then we must minus 10. 7 plus 4 equal to 11. 11 minus 10 equal to 1 with a carry of 1. Now here 1 plus 6 equal to 7. 7 plus 3 equal to 10, which exit 9. Then we must do 10 minus 10 equal to 0 with a carry of 1. Then this carry of 1 plus empty equal to 1. So this digit come from the carry. Okay, so this is the final result. All right. Then how's about the subtraction? So for example, we have a 2 input, then we have a 1 output. All of them are represented by, okay, series of digits like this. Then the question will be how to determine C from A and the B. Again, we follow this rule, okay? In case if A is smaller than B, then we must borrow 1 from left-hand side, okay? Because A is smaller than B, then the computation will be, when we borrow 1 bit, then we borrow a value of 10. Then we do this computation. C is equal to 10 plus A minus B. Otherwise, C is equal to A minus B. Okay, so here is just a simple example. Okay, for example, 95 minus 16. Okay, so at this location, you will see 5 minus 6. Okay, 5 is smaller than A is smaller than B. Then we must borrow 1 and 10 from the left-hand side, okay? So borrow a 1 with a borrow of 1, okay? With a borrow of 1, then actually we get the value 10. So 10 plus 5 is 15, 15 minus 3, okay? Give us 9, okay? Since we have borrow 1 from left-hand side, okay? Then you have negative 1. So 9 minus 1 minus 1 equal to 7. So the result is 7, 9. All right, okay? So here is one more example, okay? We have a Marian subtrahend, okay? So 0 minus 0 equal to 0, 0 minus 0 equal to 0. Now 0 minus 9. We must borrow 1 from here, borrow 1, okay? Then we get the value 10, because when we borrow 1, then we get the value 10. Why like this? Because, okay, a digit in the left-hand side is 10 times the digit in the right-hand side. We get a 10, 10 minus 9 equal to 1. Then here you will see we have a negative 1. That means this 0 minus 1 minus A. Okay, so then we must borrow. So we borrow 1 digit from the left. Okay, then we get the value 10. Then 10 minus this 1, then minus A is equal to 1. Okay, so then we move on. Here, because we have a 1 borrow, okay, a borrow of 1. So 9 minus 1 gives you the A. Then A minus 0 equal to A. 7 minus 4 equal to 3. 6 minus 3 equal to 3. So this is the final result. Okay, then final result does not have a borrow. Okay, borrow is 0 because this one is bigger than this one. Okay, so we do not need to borrow a bit from at this position. Okay, so at this position, 0 borrow. Okay. Okay, so that's about the decimal number. Okay. Then we move on in computer science, because it's quite tedious for us to write binary number. Binary number is very, very long. Okay, a lot of 111. Okay, then how to have a concise representation of a binary number? Then the answer is hexadecimal. Hexadecimal basically is to group 4 bits together to form a single value, then use a single digit to represent it. So that end up like hexadecimal. And another thing is 4 bit allow you to produce 16 value, because 4 bit can vary from 0000 all the way to FF, all the way to 1111. All the 1111 is equal to 15. So actually, 4 bit allow us to represent value which vary from 0 to 15. So therefore, we need to have 16 symbol or digit to represent hexadecimal. Okay, understand? And normally we know the 10 numeric number from 0 all the way to 9. Then there's a short of 6. Then we use A, B, C, D, E, F, the 6th letter to represent the remaining 6 digit. So for hexadecimal, the digit include 0 all the way to 9, then A, B, C, D, E, F. Okay, so when you see something like that, actually immediately you can guess out that this is a hexadecimal representation or hexadecimal number. Okay, So the principle is the same. Okay, so we use a series of a digit to represent hexadecimal number. A digit has a value and has a position, and the value in the case of hexadecimal will vary from 0 all the way to 16. Then we use a symbol A, B, C, D, E, F to represent the value 10 all the way to 15, something like that. Okay. Then mathematically, how to determine or evaluate the final value of a series of digit for hexadecimal number, then the solution is like this. Okay, so it's similar like a case of a binary number and the decimal number. Okay, now the only difference is for each digit, the value itself could be 0, 1, 2, 3, 4, 5, all the way to 6, and the A all the way to F. So you can count the number of possible value. So in total, there are 16. Okay. Then for the position I, which could be positive, if the position is in the right-hand side, left-hand side of a decimal number. If the digit is in the right-hand side of the decimal point, then the I is equal to negative value. Okay, so there's a decimal point here. Okay, so then for this case, the value should be equal to the sum of the value of each digit, and the value of each digit is equal to the value of the digit itself times the value of the digit's position. And the value of the digit position is equal to 16 raised to the power, which is equal to the digit's position. For example, at this position, n minus 1, then the value from the digit position is equal to 16 raised to the power n minus 1. Okay, so it's very much similar to the case of a binary number and the decimal number. Okay. So here I just show you, some example for you to evaluate, the value of a series of hexadecimal digit. Okay, for example, we have this series of a digit, but this digit belongs to hexadecimal number. Okay, so then how to evaluate the value? So then at this position, this is the position 0, 1, 2, 3. So it's 5 times 16 raised to the power 3. This one, at this location, the value is 6 times 16 raised to the power 2. At this position, the value is equal to A times 16 raised to the power 1. At this position, the value is equal to A times 16 raised to the power 0. Okay, then you get all this. Then you can also verify this statement. Okay, the digit in the left is 16 times the digit in the right. So you'll see this one divided by A should be equal to 16. Okay, that means the value at this position is equal to 16 times the value at this position. Okay, then for the A is equal to 10. So 10, then what is the position of this one? Is position 0, 1, 2, 3, 4, 5, 6, 7. Okay, so it's equal to 10 times 16 raised to the power 7. This is equal to 11 times 16 raised to the power 6. This is equal to 12 times 16 raised to the power 5. Then this one is equal to this is 10, 11, 12, 13 times 16 raised to the power 4. Okay, then you should be able to get this value. Okay, so I let you to evaluate the result. Okay, for the remaining two series of a digit for decimal or for hexadecimal number. Okay. Then how's about the representation of a fraction, in hexadecimal number? So it's the same like this. Okay, here I just show you some example. Okay, then the value from this digit should be equal to the value of the digit itself times 16 raised to the power, which is equal to the position of this digit. For this digit, its position is negative 1, 2, 3, 4, 5. So it's negative 5. So it's a 5 times 16 raised to negative 5 to get this value. Okay. Then 6 times 16 raised to the negative 6, we will get this number. Okay. For a times 16 raised to the negative 7. Okay. Then you will get this number. Okay. This value. Then for this one is equal to a raised to a times 16 raised to the power of negative a. Then you will get this one. Okay. So then for this, I let you to evaluate. So this should be equal 10 times 16 raised to the power negative 1. 11 times 16 raised to the power negative 2. 12 raised to the power times 16 is equal to 12 times 16 raised to the power negative 3 is equal to 13 times 16 raised to the power negative 4. Okay, so you should be able to get this result. All right. Once we know how to represent hexadecimal number, then next question will be how to do the addition with the two hexadecimal number. Okay, the scenario is like this. So basically, we need to know how to determine value C from value A and the B. Then again, we follow this similar rule. Okay, if A plus B is greater than 15, F, remember, is 15, then we just do C equal to A plus B minus 16 with a carry of 1. Otherwise, C is equal to A plus B. Okay, so here is an example. So A plus D for sure will be greater than 15. Okay, so then we just do A plus B minus 16. Then result is 7 with a carry of 1. Then 1 plus B plus A for sure will be greater than F. Okay, then we just do this 1 plus B plus A minus 16. Then result is 6 with a carry of 1. Then 1 corresponds to the value of 16. Then is equal to 16 plus 9. Then for sure it will be greater than 16. Okay, then we just do this. Okay, so 1 plus 9 minus 16. So 1 plus 9 equal to 10. 10 is represented by A. Okay. Sorry. So 1 plus 9 will be smaller than 15. So directly this is 1 plus 9 is equal to A, then equal to 10. Okay. And here F plus E for sure is greater than F. Okay. Then we just do F E minus 16. Then we get the D with a carry of 1. Then 1 plus empty equal to 1. So this is the final result. Okay. But this one, okay, comes from the carry of 1. Okay. So which indicate there is a carry of 1. Okay. All right. Then for the subtraction, we do the same. Okay. So here's one more example. Okay. So we have one input, another input. We want to add them together. Then we want to know what is the result. Okay, so 0 plus D equal to 0, 0 plus C equal to C, 0 plus 0 equal to 0, 0 plus 0 equal to 0. Then D plus A should be greater than F. Then we do D plus A minus 16. We get the 5 with a carry of 1. Then 1 plus C plus 7 should be greater than F. Then we do 1 plus C plus 7 minus 16. Then we get the 4 with a carry of 1. Then 1 plus B equal to, okay, this is wrong. 1 should be equal to C. Okay, so this is C. Okay, then A plus 0, then is A. Okay, so here is the typing error. So it's equal to 0. Here is C. Okay, all right. Then how about subtraction? Subtraction, we just apply this rule to determine C from value of A and the B. Okay, if A is smaller than B, then we must borrow 1 from the left-hand side. When you borrow 1 from left-hand side, you will get the 16. Then you just do 16 plus A minus B. Otherwise, you just do A minus B. So it's like this. Because 9 is smaller than D, then we borrow 1 from the left. Okay, borrow 1 means equivalent. We get the value 16, then 25, then 25 minus D, we obtain C. Okay, once we borrow 1 from the left, then the left become from 10 become 9 because you deduct 1. Okay, 9 is smaller than B. Then we must borrow 1 from the left. Then it's 9 plus 16 equal to 25. 25 minus B is equal to E. Then E, because we must deduct E by 1, then is D. Okay, D is smaller than F. Then we must borrow 1 from the left. When we borrow 1 from the left, actually we get the value of 16. So it's 13 plus 16 equal to 29. 29 minus F equal to E. When D, we must deduct 1 because the right-hand side has a borrow 1, then deduct D by 1, then we have a C. C minus 4 equal to 8. So this is the final result. Okay, all right. So here's one more example. Like this, we have this input minus input. Okay, then 0 minus 0 equal to 0, 0 minus 0 equal to 0. 0 minus 9, then we must borrow 1 from the left. Borrow 1, we get the 16. 16 minus 9 equal to 7. Then here, because we must deduct 1, then it's negative 1. Then it's not good enough, it's big enough to deduct E. Then we must borrow 1 from the left. When borrow 1 from the left, we get the 16. Then 16 minus 1 minus A. Then we get the 7. Okay? And then this one must deduct 1, then become A. A minus 0 is equal to A. Okay? Then A minus 0 equal to A, 7 minus 4 equal to 3, 6 minus 3 equal to 3. Okay, so this is the result. All right. Okay, so by now you know how to represent number, okay, in the memory. Okay, so we can represent integer, we can represent fraction. And then we have 3 options. We can use binary number, we can use decimal number, we can use hexadecimal number. Okay. Now we look at the conversion. For example, if one engineer use one number, another engineer use another number format, then we need to know how to do the conversion. Okay. For example, we need to know if we say we have a decimal value, then how to convert it into binary number or convert it into hexadecimal number. Okay. For simple value, this table just show you the simple conversion. 0, okay, in decimal number is represented by 000, okay, in binary number, or 0 in hexadecimal number. Okay. But for 15, for example, 15, we represent it with a series of 1, 1, 1, 1, 1. This is a binary number of 15. And for hexadecimal number is F. Okay. Then for complex number, what will be the solution? How going to do the conversion? Okay. So let's look at the scenario of a conversion from a binary to hexadecimal, because this is quite a simple case. Okay. So we apply these 2 rules to do the conversion. Rule number 1, so 1 digit of a hexadecimal number correspond actually to 4 digits of a binary number. Okay, so this is a very powerful tool. For example, when you see something like F, then immediately you know, okay, F corresponds to 1111. Okay, if you see something like C, then C corresponds to 1100. Or if you see something like 1100, then convert this into C. Done already. Okay. For example, we have this input. Okay. Let's say it's a 1111 is a series of binary number, binary bit. Okay. Then how to convert this one into hexadecimal number? The rule is very simple. Okay, because we apply the first rule. Because the 1 digit in hexadecimal number corresponds to 4 bit in binary number. Okay, then we divide all this bit into group of 4 bit. So that means this is one group, Then this is another group. This is another group. Then this is another group. Okay. Then for this group, is correspond to A. For the second one is C, and the third one is E, and the last one is F. Then the equivalent number in hexadecimal format is FECA. By convention, we use this 0 times this one. This just is an indicator to tell people this is a decimal, hexadecimal number or binary number. Sometimes we also write this with 0 times this one. Okay, just to differentiate it from hexa number. Okay, when you see something like that, for sure this is not a decimal number. Okay, so this is a hexadecimal number. All right. Okay. And then how's about inverse conversion from a hexadecimal to binary? Okay, and we apply the same rule. Just then in this case we can expand every digit in hexadecimal into a series of 4 bits. Okay, for example, if this is the input, then 6 could be expanded like this: 0, 1, 1, 0. 5 expanded. Okay, expanded into a series of 4 bits. Is 0, 1, 0, 1. B is equal to 1, 0, 1, 1. A equal to 1, 0, 1, 0. 9 equal to 1, 0, 0, 1. A equal to 1, 0, 0, 0. E equal to 1, 1, 1, 0. F equal to 1, 1, 1, 1. Okay, then replace this one by this. Replace 5 by this. Replace B by this. Replace A by this, replace 9 by this one, replace A by this one, replace E by this one, replace F by this one, then you get this binary number. Okay, so this is a conversion. So you will see it's quite straightforward when we do the conversion between binary number and the hexadecimal number. All right. Now look at the situation of converting decimal number to binary number. Okay, then our input is this one, then output must be this one. Then what will be the process for us to achieve this result? Okay, so we follow this procedure. We divide the input by 2, then the remainder is the first digit of the binary output. Then continue, then we have a quotient. Then we divide the quotient by 2 again. Then we see the remainder, we get the remainder. Remainder is the second digit of the binary output. We continue the process until the quotient becomes 0. Okay, so this is the rule for us to handle the integer part of a decimal. Then how's about the fractional part? Fractional part, we just do the multiplication by 2. Okay, here's the division. If we change division by multiply, okay, then we will obtain the rule for the fractional part. Okay, but later on we'll show you. And let's example. Through the practice of this example, then you understand that. Okay, this process. So this process is quite straightforward. Then this example help you to visualize what's happening with this process. Okay, if there's the input is 57 in decimal, then what will be the output in binary? Okay, so what we do is this is the integer because this one does not have that fractional part. Okay, so 57 divided by 2. We have this quotient plus this remainder. Okay, then this will be the first digit in the output. Then quotient first divide by 2, we get this new quotient. Remainder is 0. Then it will be the second second digit. Continue 14 divided by 2, you get the 7. Remainder is 0. Then get the second 0 here. Then 7 divided by 2, you get the 3 with a remainder of 1. Then you have a 1 here. Okay. Then 3 divided by 2 is equal to 1 with a remainder of 1. Then this becomes this one. then 1 divided by 2, then you get the 0 quotient with a remainder of 1, and this is the last remainder. Then we stop the process because we get the 0 here already, okay? The output will be 111001, okay? So it's here, okay? Then how's about the, fractional part? Okay, for fractional part, and instead of divide the input, then it's multiply the input by 2, okay? So we illustrate by this example, okay? And let's say input, we have a 0.375 in decimal. And the output, we ask you to determine what should be the output in binary, okay? So now input times 2, then we get a 0.75. Then you will see the integer part is 0, then we get the 0, okay? Then 0.7, this is a quotient. This is the result of multiplication times 2 again. Then we get the 1 integer part. Then this integer part becomes the next bit. Okay, it is 1. Then we continue. Okay, this result times 2. Okay, then we get the 1, 0, 0. Then you will see the fraction becomes 0. Then we stop. Okay, when the fraction becomes 0, then we stop. Then integer part will be the digit, next digit. Okay, then we order them in this way. This is the first position, -1, -2, position -1, position -2, -3. Okay, here is position 0, position 1, position is a digit at the position 1, digit at the position 2, digit at the position 3, etc., etc. Okay, so this is a digit at the position -1, -2, -3. All right, so output is 0.011. Okay, 0.011. Okay, so this is a conversion for the fraction. All right, and here is one more example. If we have a real number in decimal, let's say 43.167, then we must separately to do the conversion. One for integer part, another is for the fractional part. Okay, for integer part, we just do a series of division. 43 divided by 2, we get this quotient with a remainder. Then this remainder is at the position 0. Okay, and continue to do the division by 2, we get the quotient and this remainder. Now this remainder is at the position 1. Okay, let me see. Okay, yeah, position 1. Then we continue, and then this you continue to divide this, you get the 2 with because 10 divided by 2 is equal to 5. Okay, remainder is 0. Okay, then 5 divided by 2, quotient is 2, remainder is 1. 2, you get the 2. Then 2 divided by 2 is equal, remainder is 1. Then the quotient is 1. Then remainder is 0. So actually, you can continue to divide by 2. Then you get the quotient 0, then remainder 1. Okay, so and yeah, then you have a still 1 here. Okay, then you write them together should be okay from this 1 is this 1, this 1 is this 1, this 0 is this 0, this 1 is this 1, and this 0 is this 0. Because you first divide by 2, so actually is the quotient itself because for the last step, so you just shift this one to be here to be here. Okay, so it's the same. Because here we skip one step. Okay, skip one step means we do not need to do it because 1 divided by 2 for sure is 0, 1. Okay, so just treat this one as the last remainder. Okay, so this is a shortcut for you to get this one. All right. Then for the fraction, instead of doing division, we do multiplication. Okay, so 2 times this one, then we get the 0. Integer is 0. Then this 0 is at the position -1. Then this one, the result times 2 again, we get 0.668. Then this integer part is 0, then we get the 0. Then this one times 2 again, then we get the 1.336. Then the integer part is 1, then we get the 1 here, okay? Then this is a fraction times 2, then get 0.672. Then integer part is 0, then we have a 0. Then this fraction times 2, we get the 1 times, okay, 344. Then integer part is 1. Maybe we just stop at this position because otherwise you can continue. Then you get a lot of digit in the right-hand side. So we must stop at a certain position, okay? So this is position -1, -2, -3, -4, -5, okay? So this is position of a +1, +2, +3, +4, +5, +6, okay? So you put them together, you get this result, okay? So you practice, then you know the procedure well. Then, okay, you follow the procedure, then you can do the conversion, okay? So next one, how's about conversion from decimal to hexadecimal, okay? So input is a decimal number, output is a hexadecimal number, okay? So actually procedure is similar like the case of a conversion from decimal to binary, okay? So you see the procedure, divide the input by 16 instead of a 2, okay? Then we have a remainder. So remainder we have the first digit or digit at the position 0 of the hexadecimal number as output, okay? Then continue, we divide the quotient by 16, then remainder is the second digit, etc. And then repeat this process until all the quotient become 0, okay? For fractional part, we just do multiplication, okay? Something like that. So here is an example. Let's say we have this decimal number as an input. Then we want to determine what will be the hexadecimal number, okay? So first step, the decimal number divided by 16. This is a quotient. This is a remainder, 11, then represented by B. This will be at the position 0, okay? Then quotient divided by 16, we get this quotient with remainder 10. 10 is equal to A, represented by A at the position 1, okay? Then 137 divided by 16, quotient equal to A, remainder equal to 9. This is the position 2. Then A divided by 16, quotient equal to 0, remainder is equal to A. Then this is the position 3, okay? So then just write them together. It's a BA9A. So it's a BA9A. So this is a hexadecimal number which corresponds to this decimal number. Okay. Then you can verify whether the value of this one is equal to the value of this one or not. Okay. It's like A times the value of the digit times the value of the digits position. Digits position is equal to 16 raised to the power 3. Okay, then 9 times the value of the digits position. So it's 16 raised to the power 2. Then 10 times 16 raised to the power 1. And the B is 11 times 16 raised to the power 0. Then, so you see, okay, so they are equal. Okay, so all right. So this is the final output from this conversion. Okay. Okay, so the previous slide basically show you, okay, the basic way, okay, to represent, okay, number inside the memory. For simple calculation, so they are good enough. But however, for some scientific calculation, we may have a very huge number of real number, okay, and has many digits. Then in this case, if let's say our memory has a limited storage, for example, for 32 bit microprocessor or microcontroller, the basic unit of data is 32-bit, which corresponds to the 4 byte. Then the question will be, could we use 32 bit to represent a huge number. Is there a solution or not? Okay, that means expand the capability of representing real number. So the answer is yes. So we have some method to achieve, okay, this outcome. Then another issue is to represent negative number, because for scientific computation, all the data could not be positive because we have to handle negative value, John. Okay, then how to represent negative value? Okay, because in the previous slide, we know how to represent positive integer, positive fraction. Okay, we did not show you negative integer, negative fraction. Okay, so understand these two new issues: how to represent negative data, how to represent huge amount of data with a fixed number of a bit. Okay, so then we continue to study the solution, which will give us the answer to these two questions. Okay, question one, how to represent negative data. Question two, how to represent a huge amount of data with a fixed number of a bit. Okay, so in general, okay, we can use binary coded decimal to represent integer. So from a previous slide, for example, we can use 000 to represent 0, 0001 to represent 1, and this is like coding journal. Okay, so we apply this rule, then use a series of the 4-bit to represent each digit in the decimal number. Then in this way, for example, this is a decimal number. When we write in this way, we have a decimal 9,879. Then the binary representation could be written in this way. Okay, this is good for printing, but this is not good for calculation. Because I want to print something, print the 9879 on the paper, then we can do this coding. 9 is coded with this code, and 1001. This is coded with this series of 4-bit. Then during the printing, we can decode it. Okay, once I see this one, I print out the 9. When I see this one, I print out the A, something like that, for printing or display, okay, etc. Then if we have this 12,345, then we can represent it by this coding, okay? But this is only good for display printing. It may not be good for calculation, okay? And next question is then how to represent negative integer, okay? So then in this case, we can dedicate the most significant bit to serve as an indicator of positive or negative. Okay, so then in this way, so you see we use most significant bit, okay, to represent the sign, whether it's positive sign or negative sign of an integer. Okay, then the remaining bit just represents the value. So this is a simple way for us to think. Okay, maybe if we have a binary number, okay, how to know whether this is a positive binary number or negative binary number? So use the most significant bit to indicate this is a positive value or negative value. When you see this one, that means the remaining one represents a value. When you see this sign, then this is negative value. This is a positive value. Okay. So if we have a 32-bit, then we dedicate bit 31 to indicate whether the value is positive or negative. Then remaining 31 bit just to represent the value itself. Okay. So in this way, we can only represent integer which vary within this range. Okay, so it's 4,295 million. If you have a number go beyond that, then do not know how to represent it. Okay, so this is the issue. Later on, we'll come back to the solution, which allow us to solve this issue. Okay. Okay, this is appear very simple method. But researcher want to continue to improve this representation. Okay, For example, with this representation, you have 2, 0, because you have a positive 0 and negative 0. If let's say you have a 0 here, all the remaining are 0. This is a positive 0. If you have a 1 here, all the remaining bits are 0. Then you get the negative 0. That means what we waste one representation. Okay, then researcher try to see like, can we find the solution without the wasting such one representation. Okay, that means try to avoid to have a positive 0, negative 0. Then the answer is yes. People invent this 2's complement format of an integer. Okay, so then we apply this rule. So for binary number, let's say we have an n bit. Then for positive number, we just use this rule to represent the positive number. That means the sign, we have a bit which indicate whether it's positive or negative. Then we have a 0. Positive is always 0. Then use the remaining bit to represent the value. Okay. Only difference is for the negative 1. Okay. So then most significant bit to indicate this number is a positive. Then remaining one just represents the value itself. Okay. Then for negative 1, we use first bit to indicate this is a negative number. Then the remaining bit is not put the negative value itself. We just use the 2's complement of its positive 1. If let's say we want to see negative 1, actually is a 1 indicates a negative. Then is a complement, 2's complement of a positive 1. Okay, and here show you example. For example, this is a 6. Then what is the 2's complement of a 6? Okay, 2's complement of a 6 plus 1. Okay, there's a plus 1. So 2's complement of 6 is what does it mean by complement? Complement means if here you see 1, then turn it to be 1. If you see here to be 1, you turn it to be 0. If you see this 0, then turn it to be 1. If this is 1, then it become 0. If it is 0, then become 1. That means this is the 2's complement of this one. Okay, so 2's complement, then is a bitwise a 2's complement, then plus 1. Okay, plus 1, and you get this. Okay, then use this to represent negative 1. Okay, then you will see, because for the sign bit, you will always get the 1 here, because positive number is always start with 0. 0 indicates a positive number. Once you compute bitwise complement, then this automatically become 1. Then indicate to you this negative number. Okay, so then plus 1, you get this one. Then how about this one? For example, we have 102. Then how to represent negative 102? Solution is first compute the bitwise 2's complement. Okay, so 0 become 1, 1 becomes 0, 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0, 0 becomes 1. Then you see this is a sign bit, sign. Then positive become negative. Okay, then plus 1. Then A together, you get this one. So then this is a negative 102. Okay, and advantage of this representation is to have a single 0. Okay, so we use 4-bit to illustrate to you. Okay, how come we have a single 0? So you will see we can first represent positive number 0 all the way to 7. That means 0, 0, 0, then all the way, because the first bit is 0. Then the maximum value for the remaining bit is 1, 1, 1. Then we get the 0, 1, 1, 1. Actually, this is a positive 7. Okay. Then how to get the negative 7? We just compute bitwise complement plus 1. Then it's 1, 0, 0, 0 plus 1. Then it's 1, 0, 0, 1. How's the negative 6? So it's this one. Then we see we have a this representation remain here is 1, 0, 0, 0. Then we use this to indicate, represent the negative A. Okay, so you will see, and then in total we have 16 number. Okay, all of them are unique. You cannot find the negative zero. There's no negative zero because actually negative zero we name it as a negative A. Okay, so you can verify in this case. Okay, we have maximized the number of representation. Then another advantage with this two's complement format is this it will facilitate us to do the addition, subtraction, and the simple implementation of the hardware or the adder or to get the negative value of a number. So these are for the hardware implementation. Okay, so it does not concern us too much because for us, we are the programmer. Okay, so this will help a lot okay, to the designer of the hardware. All right, okay. So that help you to answer this question, how to represent negative number. Okay, then the last question will be how to represent a very, very big number with a fixed number of memory, fixed size of the memory. Okay, let's say we only have 32 bit. Then can we use 32 bit to represent a huge number or not? Okay, then the good news is yes. Okay, then we call it as a floating point number. So floating point number, that means we have a fraction. When we have a fraction, one simple solution is, again, is use a binary called the decimal. Then in this case, we can use a fixed size of a memory to serve as a representation of a digit, okay, in decimal number. But then we may use a lot of memory byte to represent a big number. So we will waste memory location. Okay, if let's say there's no concern, that means we have a lot of memory to use. Then you can use this simple method. Okay, to represent a real number. Okay, which could be very, very big, vary from a very big number which is positive all the way to a very, very small number which is negative. Okay, okay, so this is a simple way, but then our scientists always ask this question, could we have a better format of representation? And the good news is what? Is yes. Okay, that means without wasting too much memory location. There's a reason a single word, for example, 32 bit, with a register of a fixed size of a 32 bit, we are able to represent a very big number. And this invention is like this, okay? We allocate 1 bit to indicate the sign, okay, represent whether this bit is positive or whether this number is positive or negative or not. Allocate a bit to represent exponent with the base 2, okay? So then this one exponent is centered at the mid value of all the possible exponent. But here you use a bias value. Actually, is do an offset or choose the mid value. Maybe it's easier for you to understand. That means the exponent AB means what? In total, we can represent value from 0 all the way to 255. Then what is the mean value between 0 and the 255? 255 divided by 2, you get the integer. So it's 1 to 7. So the mean value is 1 to 7. So we treat the mean value as a 0. Then this allows us to vary, move towards the left-hand side, move to the right-hand side. You get it? Okay? So that means by default, 0 means 1 to 7. Okay? Negative 1 means 1 to 6. Okay? Then how to get 1 to 6 actually is negative 1 plus 1 to 7. Okay? Okay? So another explanation for this is choose the mean value of all the possible exponent. Okay? As the offset, then this offset plus the actual exponent should be the value stored inside here. Okay? Then the remaining one, we call it as a mantissa, okay, or fraction. Okay? So then the fraction should be smaller than 2, okay? Because all the exponents are here. So the mantissa in the binary number, so it's 1 point something like that, okay? So it's a fraction, it's a binary number of the fraction part, okay? Because all the integer part can represent by this information, by all this bit here. So that means here represent integer part of a real number. Here we represent fraction part of a real number. Okay. So this is an invention by scientists, and this is an international standard. Okay, we follow it, but subsequently we tell you the procedure so that you understand how to do the conversion. Let's say how to convert a decimal to exponent mantissa format. Okay. Once you know this representation, then actually you can undertake any kinds of scientific computation with a microcontroller. Okay. The good news with our Cortex M4 is that the hardware support already support by hardware the implementation of this format, exponent mantissa format. Okay. So this is why then you can you can do some scientific computation with the microcontroller. Okay, so here just show you example. That means the procedure is first we must convert decimal into binary format. It's because we actually use this to represent the integer part of the binary number and the fraction part of the binary number. Okay, so this is an invention by researcher. Okay, convert the binary number, then normalize the binary number. Normalize means what? Just write the binary number in the form of a fraction times exponent. Okay, for example, I let you to do this now. Okay, so you can convert this two integer is equal to 1 0 1 0. This is a binary number. Okay. Then 75 up to the position after that means at the position 2 after decimal point, okay, toward the right hand side. We just cut off, okay, at the position -2. We ignore the number, go beyond -2 after decimal point, okay. Then 0.75 is represented by 0.11, okay. Now this is not normalized, okay, because here you have we can take out the value which is equal to 2 with the power 1, because we must shift this decimal point to here, okay, and only have the integer part which is equal to 1. So this is normalized format. Then it's 1.011 times 2 raised to the power 1, okay. Now this is a fraction, this is an integer, okay? Then this integer has a power which is equal to 1. Then 1 plus 1 to 7 equal to 1 to 8, okay? So then you write the 1 to 8 here. And here is 0, 1, 1. Then you represent 0, 1, 1 here, use all this, okay? So 0, 1, 1, so it's here, so you see 0, 1, 1, okay? Then 1 plus 1 to 8, 1 to 7 is 1 to 8. So 1 to 8 is equal to this, okay? So you write, and this is positive. So this is the representation of this real number, okay, inside your microcontroller, okay? So this allows you to represent a very big number, okay? So it's very convenient, okay? Then here is one more example for you to practice this formula, okay? Then how about this one? Then in this case, okay, this is not the normalized one. So normalized one, so so this is first we have this decimal number in fraction. We must convert it into binary number, okay, in the fraction, the fraction part of the binary number. So and this is negative. So I let you to do the conversion. You can, okay, you times this one by 2, continue to times this one by 2. Then you get all this integer part, and the last one is you get the 1 here, okay? So this is 0.0001 in binary number. This is a 0.0625 in decimal number. Okay. Now we write it into the standard form. That means fraction times exponent. Okay. So the fraction is 1 point something. Okay. Then it's 1 point something. Then times 2 raised to the power -4, because we must shift decimal point one toward the right hand side, 1 position, 2 position. Shift 1 position will be here, 2 position will be here, 3 position will be here, 4 position will be here. That means we must shift 4 times toward the right hand side until this decimal point will reach here. Okay. 1 shift, 2nd shift, 3rd shift, 4th shift. Okay, this is why you have a -4. Okay, once you have this, then this will be the mantissa, so all 0. Okay, then -4 plus 127, then this value will be the exponent. So you write down here. So this is a exponent mantissa format. Okay, so this is the representation. This is a floating point number, okay, represented inside the microcontroller. Okay, okay. So the good news is the hardware we are happy to do it. So you, as long as you understand the working principle, it's good enough. Okay. And one more example. Let's say we have this big number in decimal. Okay. First, convert this one into the corresponding binary representation. Okay. And from this binary representation, we must shift this decimal here, 1 position, 2 position, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, must 18 times. Okay, this is why then we can write this guy into 1 point something times 2 raised to the power 18, because we need to shift 18 times toward the left hand side to obtain, because one shift give us 2, another shift we can take out the another 2, 18 shift, then we can take out the 2 raised to the power 18, 2. Okay, then we obtain this exponent. Okay, then fraction is here. Then we write down 1000 is here. This is a fraction. Then for the exponent is 18 plus 127 is 145. Then binary value is 1010001. We put it here. This is a negative and negative. So this is a the representation in the exponent mantissa format for this negative big number. Okay. Then for special case, how to represent 0? 0, okay, for sign, it could be positive 0, negative 0, exponent is 0, mantissa is 0, okay? Infinity, then we put the maximum value here and the 0 here, okay? Then just this is the representation of infinity, okay? So, and the good news just now I mentioned, Cortex M4 has a FPU, is a floating point processing unit, and the inside here it has a register. But remember, R1, R2, all the way to here are the register to this. We call it microprocessor processing unit. Okay. So it's a normal processor unit. Okay, ALU. So these are the register belong to this processing unit, but this is the floating point processing unit. Okay, so then pay attention to the name. So you see this is a single precision register, so it's 32-bit. But good news is what it supports double precision, so you can use this D0, D1. So basically this corresponds to the use of a 2 register of a 32-bit. So D0 corresponds to register with a 64-bit. D means double precision floating point, and with a 64-bit is a single precision of floating point. Okay. So then the double precision actually corresponds to the sum of the 2 single precision. Okay. And the Cortex M4 have an instruction as assembly language for you to load and add no value in the in the exponent mantissa format. So you call this one, you just put the letter V to indicate. So this is the floating point number. Okay, for example, is you get the value. When you see something like that, is the value inside register 6 plus this number. Okay, that means plus this address. The sum of this tree as address. Then from this address, you retrieve the value. Then convert this value into exponent mantissa format, right into this register. But this is inside the floating point unit, and represent it in the form of exponent mantissa format. Get it? Okay. This is inside the MPU. This is inside the FPU. Okay. MPU may stand for microcontrollers processing unit. It's a normal unit. Okay, microcontroller processing unit. FPU means a floating point processing unit. Okay, so this is belong to the FPU. When you use V here, that means this instruction will help you to do the conversion. You do not need to do anything. Okay, and when you follow this format, basically it means what? Okay, combine. This is the move. Okay, that means convert this one. Okay, from this is inside the MPU. So pay attention. All this R is inside the MPU. All this SD inside the FPU. Okay, so when you do the move, basically means what? Let this instruction to convert the value stored inside the register 11, R11 into the single position floating point register S13, and at the same time convert the value in the register R6 and store the conversion result into the single position floating point register S12. Okay, so this unit. Okay, and here one more example. Just show you. You can mix up the instruction for MPU. You can also have an instruction for FPU. If you write this format .f means it's a floating point. Okay, so for example, then convert this one. This is what when we put the hex means this is a value. Okay, direct value in the hexadecimal format. This is a hexadecimal format. Convert it into single position floating format means exponent mantissa format. So just call this, then it will do the conversion for you. Okay, so move means convert this one into here, then copy this floating single position floating point to here, then do the addition because this is equal to 1. Actually, this corresponds to the value 1. Okay, then 1 plus 1 equal to 2. Then you get what is output? Output will be 2. Okay, okay. So this is a simple calculation. Okay, and how to interpret this one? So basically means load this value into this register R0. Treat the content of R0 once you see the bracket as address. Okay, so as address. Okay, then from this address to retrieve the value, then store the value into register R1. So this is the address. From this address, get the value, read out the value, save it into register R1. Then for register R1, okay, you do the bitwise OR operation. When you do the OR operation, basically it means set the 1 to certain bit, okay, to clear a certain bit. Okay, so and then what is the mask for setting the bit? Is you create a 0, 1, 1, 1, 1, then shift the 1, 1, 1, 1 20 times toward the left hand side. Okay, then you get a 1, 1, 1, 1. In the right hand side, you have a 20, 0. Okay, so then you in total, then you have 24 bit. The first 4 bit is 1, 1, 1. The remaining 20 bit are 00, because when you do this shift, then you shift in 20 bit 0. Then you have a 24 bit, then you do the OR operation with 24 bit inside the register R1, then resolve, store into the R1. Okay, then the final result from R1 and the store back to the memory location. Okay, at this memory location. Okay, so this is meaning of this instruction. Okay, so you and this one just for you to understand the use of single precision floating point format or exponent mantissa format. Okay, but anyway, we will come back to this instruction in subsequent lecture. All right. Here is one more example. So you will see we have a move, we have a store, we have a move. Okay, that means copy over the content from register R3 right into the floating point register S3. Okay, then here is to load this value. Okay, but here you will see equal. You can exactly write this is a single precision. Okay, it's a real number. Then and load it, store it into the single precision floating register. Okay, then this one is to override. Okay, move. That means okay, move the content. Basically, move the copy the content here, convert it back into the normal. Is a decimal number format, and write the value into the register R4 of MPU. This is the way for you to do the conversion from single precision floating point format and back to the normal normal hexadecimal format. Then you can analyze the value here R4. Then you see how it looks like. Okay, all right, something like that. Okay, so that's all for today's lecture. So today's lecture is very important, and this knowledge allow you to understand the way for us to represent data inside the microcontroller. And you can also apply the learned knowledge to do the manual conversion of the number among the different formats. So we have a study binary format, decimal format, hexadecimal format, and also the two's complement format plus floating point format, which make use of the IEEE standard, which is called as exponent mantissa format. Okay, then subsequently we are going to study how to read in the data, how to send out the data, how to do the data processing. Because by now we know, okay, what is the hardware that you are going to use, then what is the memory, how memory is being organized, okay, and also you know how to represent data inside the memory, how to represent instruction inside the memory. Okay, so now you are ready to study how to get the data into your microprocessor system, how to send out the data from your microprocessor system, how to process the data inside your microprocessor system. Okay, so we still have 3 lectures from me. So after my lecture, then you will continue with Professor John Han to study the application with the interface for input and the output device. Thank you for your attention, and see you in the next lecture.